So good morning all of you. So now that quiz 1 is over, I am sure that many of you are feeling a little bit familiar to whatever we have covered until now. So that was on external boundary layer flows, external laminar boundary layers. So from today onwards we will start looking at internal flows. Okay, internal laminar flows. Internal flows are very important as far as engineering heat transfer is concerned, because most of the heat exchangers that you are looking at, the tube in tube heat exchangers, shell in tube heat exchangers, so they are all having internal flows. And how do you design these heat exchangers? Once you know the corresponding relationship between the Nusselt number and the flow conditions, such as given by the Reynolds number as well as the properties given by a Prandtl number. So you have to develop suitable correlations between linking the heat transfer coefficient and the flow and the properties in some manner. So we will look at developing such kind of correlations for internal flows. So far we had developed these correlations for external flows. The technique for internal flows are a little bit different, not exactly like the way we are going to do external flows, where we had a clear boundary layer kind of a flow pattern. So we were giving boundary conditions like at y equal to 0 you have whatever temperature, and away from the wall you are giving free stream condition, that is y going to infinity, far away you are giving the free stream condition. But in the internal flows there is no classical boundary layer kind of a pattern that you can follow, especially when the flow is developing fully developed. So there in those regions you cannot look at regions which are far away from the boundary layer, because in the case of fully developed flow everything is boundary layer itself. Okay, the boundary layers from the bottom wall, the top wall of a channel can merge, and they can, everything will be a viscous region. And same way in a duct you can have boundary layer growing simultaneously from all the walls of the duct, and you cannot really go and identify a point where you can look at potential application of potential flow and things like that. So therefore the solution procedure for the laminar internal flows are slightly different from the external flows. So therefore we will start looking at some basic aspects of internal flows before going into the mathematical theory of how to solve the laminar internal flow heat transfer. I think most of you are familiar with the basics of internal flows from your fluid mechanics classes and your earlier heat transfer class. So I am going to give an overview, very brief overview, and we will look at basic fully developed case first, okay, where we can get the solution for velocity profiles very easily, okay, and then we will slowly gradually go to the case where we have heat transfer. So we will look at different regions again. So first we will start with the simplest case, that is both hydrodynamically and thermally fully developed case. Okay, so before doing that, let me give you some kind of an overview to laminar internal force convection. Okay, so classically I would like to illustrate internal flow by means of flow between two parallel plates, or flow you can take a sectional view of a duct and then look at how the flow pattern is. So here when the flow is entering the inlet of the duct, so you have a uniform velocity across the cross section, and then you see a boundary layer growth from, say, the two walls of the duct like this, and this growth keeps going on till a particular location which is at the center of the duct diameter. Okay, so exactly at the center the two boundary layers will merge, and after that the region whatever you are looking here, it's completely dominated by viscous effects. So whereas at the inlet you have a very small region close to the plates where your viscous effects are important, outside still the potential inviscid flow theory is valid, whereas once the two boundary layers merge, in this particular region everything is viscous dominated. Okay. Now if you look at how the profiles are drawn, somewhere at the inlet you can have a profile something like this. Now as you keep going downstream, the gradient becomes better and better. Okay. So as you keep going downstream, the gradient becomes lesser and lesser. Here you have very high velocity gradients at the wall, and slowly it gets smoother and smoother. Now once you reach this particular zone here, both the boundary layers merge and the velocity profile becomes what is called a parabolic velocity profile. Okay. So therefore, looking at the different regions here, you can classify the flow based on whether you are looking from the entrance till the region where both the boundary layers meet. Okay, from the entrance of the duct. So this region, this length is called the hydrodynamic entrance length. Okay, so you can use the notation L subscript H to indicate that this is a hydrodynamic entrance length. We will also have a similar entrance length for temperature profiles. So after the two boundary layers meet, now the velocity profile looks similar wherever you go downstream. So it all becomes parabolic velocity profile, and this region is called fully developed region. So therefore you can classify the different regions of laminar internal flow. So now you can look at this region as entrance length region or entry length region, or hydrodynamically developing region. Okay, so therefore here you can see the boundary layers thickness is a function of position. Now once it merges, then everywhere it is viscous dominated and the velocity profile is invariant of the axial location, alright, and this becomes completely fully developed. So this is the characteristic of internal flows, and in order to really understand how to calculate the length, the hydrodynamic entrance length, there are several hand waving correlations. There is no exact rigorous theory to determine the entrance length. Okay, strictly speaking, you have to solve the equation and understand where the velocity profile becomes parabolic and becomes invariant. Okay, so just to give a empirical thumb rule for laminar flows, the non-dimensional entry length, so this is non-dimensionalized by the diameter if you have a duct or if you have a channel. So this is the separation between the two plates of the channel. Okay, so LH by D is roughly 0.05 times RE based on the diameter of the duct. Okay, so here the Reynolds number for internal flows is defined based on, so how do we, what kind of characteristic velocity that we have to use? That is the question. So the kind of an average, because here you see, even if you look at a fully developed case, you have a profile which is a function of y. Okay, so you don't have a fixed velocity value like in a case of external flow, like a free stream velocity. Therefore, so you can use what is called a mean velocity, which we will define shortly. Okay, so this is your mean velocity. So if you replace this parabolic velocity profile with a constant profile everywhere across the cross section, so this is referred to as the mean velocity. So naturally, how you have to define the mean velocity? Volume flow rate or the mass flow rate has to be constant. Okay, so therefore the mass flow rate defined by this, let us say rho into um into the area for a circular duct, the area is pi into r naught square. Okay, where r naught is the diameter radius of the duct. So this should be equal to the flow rate obtained with this particular profile, parabolic profile. So that is rho into u into, now if you say area is equal to pi r naught square, my dA will be equal to 2 pi r naught dr naught. Okay, so I can average this, integrate this over the entire cross sectional area. Okay, so this will be 2 pi r naught dr naught. Correct? So I have to integrate from, so if I take the coordinate from the center, my radius right from the center, this is 0 and this is r naught. Okay, so I integrate my profile across the entire cross sectional area. So that will be rho u into r naught into dr naught. So this will give me the mass flow rate, and this mass flow rate given by this profile should be identical to the mass flow rate if I replace this parabolic profile with a uniform velocity. Okay, so from this I can define my mean velocity or the bulk velocity. Okay, my pi cancels, so this is if you look at incompressible flows, my density is also constant. So therefore this will be 2 by r naught square. So here my r naught, so this is basically my r, I'm sorry, this is pi r square. Okay, so this should be 2 by r naught square integral 0 to r naught u into r dr. So this will be the definition of my mean velocity, or what I call as bulk velocity in internal flows. Okay, so this will be used as a characteristic velocity to define my Reynolds number, and it's also based on the diameter of the duct divided by the kinematic viscosity. Okay, is it clear? Okay, so this is the area of at any location r. Okay, so if you look at any location r, so this will be the cross sectional area pi r square. Okay, so this is what I'm using it. So if I look at any differential area, that will be 2 pi r dr. So I have to integrate it over the entire cross sectional area. So that's why I'm doing this integral right here. Okay, now based on the Reynolds number, you can again classify. Now when I say that for laminar flows, this is the relation to calculate my entry length. So how do I first determine whether the flow is laminar or turbulent? So once again I use the definition of Reynolds number to check if it satisfies a certain cutoff or a critical Reynolds number. Okay, so for typically duct flows or flow between two plates, the critical Reynolds number for transition to turbulence will be approximately 2300. Okay, this is once again an approximate value. You know, it need not exactly become turbulent at 2300. In fact, if you maintain the walls of this channel to be extremely smooth, it can remain laminar even as high as 7000 or 8000. Okay, so if the turbulent intensity at the inlet is so small that it cannot trigger early transition to turbulence, and if the walls of the channels are very smooth, it can go as high as the critical value can be as high as 8000 or 9000. Okay. So if you check your RED is less than RE critical, so this is an approximate thumb rule for classifying the flow as laminar. Okay. And otherwise you can look at either in a transition regime or in a turbulent regime. Okay. As far as laminar flows are concerned, this is the thumb rule for calculating the entry length. All right. And for turbulent flows, interestingly, what happens? The entry length ceases to be a function of Reynolds number. Okay. So the entry length non-dimensionalized comes out to be approximately some 10. Okay. So imagine that you have a Reynolds number of say 3000. Okay. If you classify that as a laminar flow, thinking that the flow is still streamlined enough to be classified as laminar, so there what should be the value of LH by D? 15. Okay. Now in the case of turbulent flows, if suppose the 3000 was now turbulent, the LH by D would be 10. So now you can infer that the entrance length for turbulent flows is actually smaller than the entrance length of laminar flows. Okay. So the reason is the turbulence promotes lot of intense mixing or diffusion of flow. So the mixing takes place due to the gradients along the y direction. So there will be intense mixing, and therefore the profile can reach a fully developed state much earlier in the turbulent case than in the laminar case. Okay. So therefore the entry lengths are much smaller in the case of turbulent flow than the laminar flow. So now the condition that you have to apply to determine that the flow is fully developed. Okay. Now you can see from the shape of the velocity profile that if you plot this velocity profile somewhere downstream, they are going to all look very similar. So we have to introduce a mathematical criteria. Okay. So what should be the mathematical criteria? How do I say that I am in a fully developed region, for example? Yeah. So you look at the velocity profile. If the gradient with respect to the axial direction, this is my axial direction, x, this is my radial direction. If this is 0, so this clearly tells me that I am in the fully developed region. Okay. So this is the criteria as well as the flow is concerned. Okay. Now associated to the flow, we can also have heat transfer. Now in the case of heat transfer, suppose I take a case where I have Prandtl number greater than 1. Okay. So I have a growth, suppose I apply either a uniform heat flux or a uniform temperature to the duct walls. So either I say Q wall in either of this case. Now associated to the boundary layer growth of the velocity profile, you can also have a thermal boundary layer growth. Now if my Prandtl number is greater than 1, my delta T will be less than delta, and therefore if you see the growth of the thermal boundary layer, it will be smaller than the velocity boundary layer growth, and therefore the point where they merge also will be slightly downstream than the hydrodynamic entry length. Okay. So somewhere they will be merging here. So this will be my delta Tx. Now, so similar to the hydrodynamic entrance length, I can also define what is called as a thermal entry length, the point where the two thermal boundary layers merge. Okay, I can use the notation L subscript T to say that the length corresponds to the thermal boundary layer. And if I draw the profiles, okay, so typically if I draw a profile somewhere here, So now the wall temperature is higher than your bulk temperature or the temperature of the fluid inside, so it should look something like this, right? So the magnitude of your wall temperature will be higher than the magnitude of the temperature of the fluid at the center, correct? So this will be your temperature profile, T as a function of Y. So now when you say that you have a hydrodynamically fully developed region and you have a hydrodynamic entry length, similar to that you have a thermal entry length, okay, and you should also have a thermally fully developed region, okay, just analogous to your velocity profiles where the velocity profiles are invariant of the axial location. However, you can very clearly see when you apply heat transfer, okay, for example, if you apply a uniform heat flux, what happens? The wall temperature keeps on changing with respect to x. The wall temperature will not be the same, for example, at the entrance and somewhere downstream, because you are continuously adding heat. So therefore, due to conduction, so the wall temperature has to keep increasing downstream, and also consequently the fluid also keeps getting heat continuously. So the fluid temperature also has to vary along the x. So therefore, unlike the velocity profile which shows a constant behavior, the temperature will never be a constant value, correct? So you will find the temperature of the fluid anywhere that you plot will keep on changing with respect to x at any y location, or even at the wall that also keeps changing. So how do we now look at a region and tell that that region corresponds to thermally fully developed? Okay, so the criteria is we have to now develop a definition to call a thermally fully developed region. Okay, so how do we now use that criteria? Okay, so thermally fully developed. So I know that due to heat transfer, my wall temperature is a function of x, it keeps changing. My fluid temperature anywhere is also a function of both x and r. Okay, now I have to, same way, similar to the way that I have defined what is called a mean velocity, now I have to define another velocity which is something similar to a free stream velocity in external flow for internal flows. Okay, so I will define what is called as a mean temperature. So I need all of this to define a non-dimensional temperature, correct? So I need to define another mean temperature. Now this mean temperature should be a function of only x. So therefore it has to be constant, again something like this, right? So this should be my mean temperature. The same way I define my mean velocity based on continuity principle. I have to define the mean temperature based on what? Energy conservation. So what I should say is that the enthalpy of this uniform temperature profile should be the same as the enthalpy of the actual profile that you are getting. Okay, so how do you now define enthalpy? Based on the temperature Cp T. Now this is the specific heat capacity, so the total enthalpy will be, you have to multiply by the mass flow rate. Now this is the average enthalpy if you replace the temperature profile with the uniform profile, correct? Now that should be equal to the enthalpy of this varying profile. How do you calculate the enthalpy of that? Integral 0 to r naught. So Cp, my m dot now will be, now there is a velocity profile also here. Please remember, corresponding to this temperature profile there is a parabolic velocity profile. So my m dot there will be rho u into, you have already dA which is your 2 pi into R dr. Okay, and of course you have your temperature into the enthalpy. So this will be T into R dr. So this is the balance of enthalpy. No, so this is satisfying enthalpy conservation. Okay. So therefore, for an incompressible flow with constant property, you can. So this is nothing but your. Okay. So let me just write it right now. So I can knock off this, and my Tm will be 2 pi integral 0 to R naught. I can take my rho out. So T into U into R dr divided by. So my flow rate there again will be a parabolic velocity profile. So I can write this as integral 0 to R naught into U into R dr, right? So I will have a 2 pi into rho again. So these will get cancelled off. So therefore, this will be 0 to R naught. You have T into U into R dr divided by integral 0 to R naught U into R dr. So this is my definition of my mean temperature at any axial location. Mean temperature, or sometimes people refer to this as bulk temperature. Sometimes they also refer to this as mixing cup temperature. So there are different names to the same mean temperature. So this mean temperature is defined based on the enthalpy conservation. The enthalpy, if you replace your varying temperature profile with a uniform temperature profile. Okay. So therefore, now we can see that we have defined all our necessary temperatures here. So you have T wall, which is a function of x, Tm, which is a function of x, and you have T, and therefore we can define a non-dimensional temperature theta, just similar to the external flows, where we defined as T minus T wall by T infinity minus T wall. We can define T minus T wall. So T is a function of both x and r divided by T mean minus T wall. Okay. So once you define a non-dimensional temperature profile like this, now we can look at a region where this non-dimensional temperature profile is invariant of x, because in that region your T minus T wall will be a particular function of x, Tm minus T wall will be a particular function of x, such that the numerator and denominator are vary in the same way. So therefore there will not be any variation of theta with respect to x. So the condition for defining thermally fully developed flows will be d theta by dx should be equal to 0. Okay. So once I identify that region where my d theta by dx is equal to 0, so then I can call that this is a thermally fully developed region. So I have to monitor my temperature profile theta, non-dimensional. So if I plot the non-dimensional profile, so although the dimensional profile will be something like this, okay, the non-dimensional profile will be something similar to the velocity profile. Okay, so at wall it will become 0, right at the center it will be T mean. Okay, so therefore it becomes so it will be something like this. Okay, so you have, this is your dimensional profile and this is your non-dimensional profile. This is your theta and this is your Now once you plot theta, okay, so this theta should be only a function of r now in the thermally fully developed region, because it doesn't, the non-dimensional temperature profile now should not vary with respect to x. That is the condition which satisfies the thermally fully developed region. Okay, so this should be a function of only r. Now based on this we can now define a criteria for the heat transfer coefficient in the fully developed region. Okay. So therefore in the thermally fully developed region, my theta is a function of r only, whereas in the thermally developing region here, thermal entrance length region, my theta is a function of both x and r. Okay, but once it becomes thermally fully developed, it doesn't become a function of r, x, it is a function of only r, provided your velocity hydrodynamically is fully developed. Okay, so this is a condition provided you are hydrodynamically also fully developed. Okay, so it should be hydrodynamically fully developed first, and that's where we have taken a variation like this. We have a parabolic velocity profile, and on top of it, if you put a condition that d theta by dx is equal to 0, so then you are looking at a location where your theta is a function of only r. Okay, so for this particular region, you can calculate your heat transfer coefficient as minus k dt by, so now it is not y anymore, it is r, and this will be at r equal to r. The heat flux wall heat flux should be at r equal to r naught. Okay, now you have to be careful with the sign, because the coordinate is going from the center, it's not coming from the wall. Okay, so therefore you see the temperature profile increases, the temperature increases with increasing r, so you don't have to put this negative sign here, the gradient will be anyway positive. Okay, so whereas if you have a coordinate from like this, then the gradient will be negative, so you have to put a negative sign. Okay, so now your coordinate system is from the center of the duct, so therefore you can just say this is k dt by dr at r equal to r naught divided by T wall minus T mean. This is how you define your heat transfer coefficient for internal flows. Okay, so now we can write this in terms of the non-dimensional temperature. So I can write this as d by dr. Since this is a derivative with respect to r, and T wall and T mean, they are functions of only x. Okay, so they can be directly taken inside this, and you can also introduce T minus so T minus T wall by Tm minus T wall, and you can put a negative sign here. I am just flipping this as T minus T wall. Okay, so since T wall, Tm, they are only functions of x, I can just introduce this as T minus T wall by Tm minus T wall, which is the same as this, correct? So this is nothing but theta, so this will be minus k d theta by dr. Now this is at r equal to r naught. Now if you look carefully, my theta is a function of only r. Okay, so therefore the slope of the profile at r equal to r naught, that is the slope at the wall, so that also has to be a function of only, that is a fixed value. The slope at any point will be a function of r. At the wall, that will be a fixed value. Now since theta is not a function of x, so the slope also cannot be a function of x. Okay, so whatever slope I calculate with respect to the profile, whether it is here or if I use the non-dimensional theta, so the slope I calculate will be the same, because the profile is going to be the same. The slope here and here, they have to be identical. So therefore, so this d theta by dr at r equal to r naught has to be a constant value. So which tells me that my h is a constant, so therefore it's not a function of x. So this is a very, very important conclusion. So as far as laminar internal flows, both hydrodynamically and thermally fully developed, so your heat transfer coefficient will become a constant. It's not a function of x. So that is going to simplify your correlations very drastically. Okay, so this is a very important principle, and this doesn't depend on the boundary condition that you employ, whether it is a constant wall temperature or constant heat flux. Irrespective of that, we have not used any boundary conditions here. Irrespective of the boundary condition, this is the fact that your heat transfer coefficient is a constant for laminar internally fully developed flows. Okay, so with that, this kind of gives you a brief overview what we are planning to do, and in this particular, the next 9 hours or so, we will focus on 3 regions. So first we will look at what is called region 3. Okay, so let me identify this. This is region 1 right here, where your velocity hydrodynamically is growing and also your thermal boundary layer is growing. This is your region 2, where your velocity hydrodynamically has developed, but your thermal development is still underway. Okay, now this is your region 3, where both the boundary layers have merged and both the hydrodynamic and thermal boundary layers are fully developed. Okay, so therefore the first part of the course will be on region 3, which is fully developed both hydrodynamically and thermal. And as you can see, that is the simplest to start with, because you have constant heat transfer coefficient, so you can calculate the velocity profile, the temperature profile, and for a given boundary condition, whether it is a heat flux or a wall temperature, you can identify what is that constant value of h. Okay, so then slightly more complicated is region 2, where you have fully developed hydrodynamically and thermal entry length. So here your velocity profile is fully developed profile, but the equation that you are solving doesn't have that condition d theta by dx 0. Okay, and finally the most complicated region is region number 1, where you have both hydrodynamic and thermal entry length. So this region you cannot get a good closed form analytical solution. You have to solve the complete Navier-Stokes equation, because you cannot neglect any terms. The gradient of velocity is not 0, the gradient of non-dimensional temperature is not 0, so therefore all the terms in the Navier-Stokes equation has to be present. You cannot neglect any of the terms, and therefore you have to do a complete numerical solution for region 1. Okay, so in this particular course we will be focusing on region 3 and then lot of problems related to region 2. Okay, so we will stop here, and tomorrow we will look at, we'll start of course with region 3. We will look at the solution to first the hydrodynamic fully developed condition, get the velocity profiles, and then depending on the thermal boundary condition we will also get the fully developed temperature profiles.